So in continuation of the parallel forces in a plane, we are trying to solve one more problem which we have taken the beam in the horizontal direction. So here the problem statement, a beam ABC. So the beam name itself is the ABC, is supported and loaded as shown in the figure. So that means some of the details are revealed in that figure. Find the reactions at the supports. So we need to find out the reactions at A as well as the C, B as well as the C, because there is no reactions over here, because there is no support, only the load is acting, and only the reactions at B as well as the A we need to calculate it. So then how could you calculate the reactions? As we know that we need to draw the free body diagram in this case. As we know, can you see here that load is going to be acting at 1000 newtons, right? And the B is going to be at the point is here, that's the support, and at A. As we know that when there is a hinge, support is there, it's trying to restrict the two types of the motions that we studied. One is the horizontal direction, one is the vertical direction. It is in upward direction or downward direction, that's we need to decide. That is also depends on the load is acting on that member. Suppose in this case, the load is acting vertically in the downward direction. It means that this hinge is going to be supported to one type of motion. So that's we need to find out. And the B is going to be acting like a fulcrum. It's trying to, the motion we need to find out. So for this, I'm going to be taking the load, I'm going to be applying here. So that we found that this motion is going to be, we need to find out. So when I'm going to be applying the load, because of this point is going to be acting like a fulcrum, is trying to move in the upward direction. That means the point A is trying to move in this direction. That motion is going to be consist here. At the same time, the body at the point B, so the load is acting in this direction. This position is trying to move in the downward direction. So once we are finding the displacement of the beam, that is the virtual displacements, once we are going to find out, then we can draw the free body diagram very easily. So in this case, what will happen? I'm going to be taking the axis of this member. So the same axis I am going to be taking here, which representing the beam. So this is going to be the beam, and this is going to be the axis of this member. So then in this case what will happen? That load is going to be acting at this point is going to be the 100 newtons. At the same time, at the point B, that the motion of the beam is going to be existed in the downward direction, but the reaction forces are coming from this point is in the upward direction. That means always the reaction forces opposing the motion of the body. That means we are providing the constraints or the restrictions to the motion of that body. So then this is the RB is going to be acting. But in this case, can you see the motion is going to be upward direction. We need to show in the downward direction. So this is going to be your RA. The distance between these two is going to be the 1 meters and 0.25 meters distance it is existed. So now we are considering the system is in the equilibrium condition. Then we will take the equilibrium equations of equilibriums. So that's going to be, we are going to do sigma f of x equal to 0, sigma f of y is equal to 0, and moments at a point is equal to 0. So then in this case, first I am going to be considering f of x. So in this case, there is no forces in the horizontal, then it is not going to be valid here. So then forces in the vertical direction, that is equal to 0. So in this case, can you see how many forces are acting vertically and downward direction, so that we will understand the sign conventions. So RB acting the vertically, these two forces acting in the downward direction. So that I am going to be taking RB is equal to, that's going to be RA plus 100 newtons. So this is the equation 1 suppose. So in this equation we got the equation of equilibrium when the body is trying to move in the translatory direction. But in this case what will happen, in the single equations two unknowns are there, then again we need to go with the moments at a point A or at the B. So that what will happen, because the same force is going to be passing to the point of our observation, then there is no perpendicular distance, then automatically that force is going to be 0. For this time being, the moments at A is equal to 0 I am going to be considering, that is the equilibrium of that part. So then what will happen, when I am going to be considering this is the part, so we are understanding this RB is going to be moving in the counterclockwise directions, and this 1000 is going to be moving in the clockwise direction. As for our terminology, which is moving in the clockwise direction, the moments we can say the positive, and RB is going to be moving in the anti-clockwise direction, that is the negative. For this one, I am going to be taking here is going to be 1000 into, what is the distance between the point C to A? So that's going to be your 1.25 meters we have. right? So that is equal to, because it is moving in the counterclockwise, that's going to be RB. What is the distance it is existed? 1 meter we do have. So then finally RB is equal to, what is the formula we do have? 120. So that's going to be, we have here is the 125 newtons, we got it. RB is equal to how much? That is the 125 newtons we had. So when I am going to be substituting this equation, so then what will happen? I will get the RA. So that's going to be RA is equal to RB minus 100. So that's, I am substituting RB in the equation 1. So that is going to be 125 minus 100. So then finally RA is equal to 25 newtons, I got it. So this way we are going to be solving the reaction forces at B as well as at A.